Hello, everyone. This is Jay McCarthy, the CTO over at Reach. Um, there's been some requests to get kind of a walkthrough of the code for HumbleSwap, so that's what we're going to do today. And just jump right in. You see right here is the editor that I use for writing all this stuff, and I'll just sort of walk through from the code. Um, I'm just going to sort of fly by the overall structure and then we'll dig into some details. So we define a little helper library of just some general tools that are useful in this program. And then we define some structures that are going to be common throughout all of the HumbleSwap code. Then what we do is we define the DAO, which we call the Triumvirate. And then after defining the DAO, then we define the actual logic of Humble, like the core ways that it mints and manages a pool. And then from there, we define the actual swap. This is a one contract per pool. And then there's a lot of code for this. Once we get through to the bottom, then we define the actual swaps, one for when we use an algo and an ASA, and one for when we use two ASAs. And then we define a little application that is just for getting access to the library. Because one of the things that Reach can do is that it can turn this code, like any helper function, it can turn it into JavaScript that is called directly from our UI. So that way we don't have to write the code once. So that is sort of the high level of this 530-ish line program. And so what I thought that I would do first is we'll zoom in on the swap. So notice that what I do is I define a function that's called swap. And what this is going to do is it's going to return a new pool, and it returns one that is based on this true or false. That way we only have to write the code once, but it actually works on either algo or ASA or ASA and ASA. So this is the definition of that function is right here. So swap is a function that uses network and returns an application. And what we're going to do is there's going to be some APIs. So there's the provider. That's the person that's the liquidity provider. They can withdraw and they can deposit. Now notice that when they withdraw an amount and they get back a balances, or they can deposit a balances and they get back an amount. So what's balances? So balances is a structure that talks about a pair of balances, one we call A and the other we call B. Then we're going to define what the token is. And so token A is going to be a type for token A. It's either going to be null when we use the network or token otherwise. Then there's the admin participant. This is like the person that actually launches the token. So they're going to provide a token A, a token B, a name that they want to provide, and a symbol. They're going to have a function that gets called when the pool gets created, and then they're going to have a contract for the protocol. That is the DAO/the Triumvirate. There's a function called swap, which takes two numbers and swaps them and returns a balance, and this can be called by the trader, and they can either be swapping A for B or B for A. Finally, there's an API that you deal with the protocol with. So there's a function called protocol delete, and then the pool interface. So let me just show you what the pool interface is. The pool interface is that there's a harvest function. Harvest can take an address and the new protocol information, and it returns a balance and a number. Finally, the last sort of things to talk about are the info that we provide access to. So there's information about this particular pool, like what its liquidity token is, what its balances are, what the protocol information it's dealing with, what the balances are for the protocol fees, and what the two tokens are. This information is basically stored in the global state, if you're familiar with the details of Algorand contracts. There's a function called view that provides access to this, and then there are events that we generate for either harvests, withdrawals, deposits, or swaps. Lastly, we set the verify arithmetic option. Verify arithmetic makes the program take a lot longer to run. It's a lot longer to verify, so we only turn it on every once in a while when we make big changes. There's also another verification property that there's this variable called check the big one, and that makes it also take a lot longer. So what we do is part of our testing process, we do that, but we don't have them enabled on kind of a day-to-day basis. All right, so now like what's kind of the structure of things? So what we do is we define this function that's called check the input, which basically says, is the number on this platform big enough? And if we're not on the network, are the two tokens not the same thing? Because we're going to manage, one of the things that Humble needs to do is it needs to make sure that it like opts in for the two tokens, and we don't want to try to opt in twice and make people pay for more if they're the same thing, so we make sure that they're not. The admin then declassifies and shares all the information about the pool that's about to be created. And then what we're going to do is we're going to create some helper things that helps us deal with having one piece of code for the two different kinds of pools. So there's going to be something called tokat, and that is a tuple that stores token A, if it's a token, and then there's token AM, so that's a maybe that is wrapped around the token, and then if there is no token A, then that's none otherwise. We go off and we call the protocol to get the initial information about the protocol. This is the register function. We figure out what our initial balances are. They're going to be 0 because the pool started with nothing. We have an initial supply of the new liquidity token. We're going to have these two variables called LP held and LP minted. So we hold the entire supply at the beginning. We make the pool. Now, here's kind of another helper function that we're going to have this helper function called pay expression that's going to take in an amount of liquidity tokens, A's, B's, and rewards to pay. And if we're using the network token, then the A and the rewards go together as the first field. But if we're not, then the rewards are only in algos, and then token A has its own field. So this way we can basically use pay expression everywhere, and we don't need to have lots of code in multiple places at the same time. Okay, then pay balances just calls pay expression, but it uses one of these balance data structures because we use that all over the place to simplify the code. Then we signal that the pool is made, and that code that I just ran through, like every time you click make a pool on Humble, it calls this. It makes up a new contract, registers it, and then signals. I'm going to pause going through the pool code and jump over and see what happens over here in register land. So what's going over here for register land? Well, one of the things that Humble does is that, as I said, there is a DAO that manages everything. And so we call that the Triumvirate. And so the Triumvirate is another application, and it has triumvirs. These are the initial people who are in control. And the admin, basically what they're going to do is they're going to say who those are. And then there are these commands that can run. These are the actions that the triumvirs can do. They can either do nothing, make new triumvirs, make new protocol information, harvest protocol rewards. They can give rewards to an address, or they can kill the entire system. And triumvirs, they have a way to either propose a command or run a command. And then the most interesting thing that happens is that individual instances of the protocol can call the register functions. So we're going to ignore all the details of the triumvirs and just jump down to that one. So when the triumvirs start, there's a certain fixed protocol information, which is that it's not locked. The total fee is 0.03%, where the liquidity providers get 0.25%, and the protocol itself gets 0.05%. And so that protocol information, that's going to be stored in this parallel reduce computation, where we're storing whether we're done, who the triumvirs are, what the commands are, and what is the current info. And we're just going to zoom in to register for now. So this right here, this is the code that gets run. So see how we have a remote object, which is the protocol. We call register on it. So what is that function? Is this function right here. So we have a new contract. We have what its token A is and what its token B is. And what we do is we say, okay, well, who's calling us? We're going to make sure that the contract and their address match. Then what we're going to do is we're going to, return the current information to them. and we're going to emit a register event, and then that's it. So anyways, so that's just what happens. So when you go to Humble and it looks for all of the pools, what it's doing is it's looking for these events. It's looking for all the things that got registered, and it is keeping track of a little database in your browser of all the token A B pairs, and it won't show ones that if someone would like try to get around our interface and create two instances of the same one, it'll just ignore them. It'll just ignore the second. All right, so anyways, so now we're ready to go. Okay, so basically what's going to happen in the pool is that we're going to repeatedly go through all the bunch of options, remembering these things, whether we're done, what the pool balances are, what the liquidity token balances are, what the current protocol information is, and what the current protocol balances are. And those are all initialized to these initial things that we walked through. There's going to be some helper functions that we're going to provide. So for instance, we have, like, is something 0? Are we locked right now? What are the balances? We want to have a function that can update the liquidity, and we have a function that will call when liquidity comes in, and another function that calls when liquidity comes out. And then we have this kind of complicated invariant. So an invariant is a proof that we're proving about the program. So we prove that if you're not using a network token, then the balance is always 0. We prove that the supply of the pool never goes down. We never burn anything. We prove that we never destroy the pool. These are the liquidity tokens. We prove that the total supply is always equal to how much is held and how much is minted. We prove that the balance of the pool is equal to how much we think it should be held. We prove that the balance of token A that we hold is equal to how much the pool holds and how much the protocol holds. The balance of B is how much the pool holds and the protocol holds. We prove that there's an invariant on the fees. So this invariant on the fees, I'll show you what it is. It's that the fees can never exceed 1%. I always forget if this is 1% or 0.1%, because, but whatever. We prove that it can never exceed 1, and we prove that the total fee is always equal to the two fees, and that there always has to actually at least be a fee. It would be nice to not require that there's a fee, but we have got to divide at some point, so that's why there's a requirement. Anyways, we also prove another property. This is kind of meaty. It says that if we're done, then that means that we're locked and the liquidity that we've minted is 0, and the balances of the pools and the protocols are also 0. So this basically says that this function can only ever end if it has been explicitly locked, if everyone has explicitly retracted their liquidity, and thus we've zeroed out everything. So this is like a safety check to make sure that there's no way for the pool to die and anyone to still have claims on it. So now what we do is we have some helper functions about, we basically have the implementation of harvesting. So every function kind of looks similar, which is that it's going to have the function that we're calling. So harvesting, this is what the protocol does. You can see there's a little comment that says there's an error in my code generation. So I really wish that I could make the code more beautiful, but I can't, so we'll fix that eventually. But anyways, so basically how to harvest, we make sure that we're being called by the protocol address. We check to see if the fees are correct. What does this mean for fees to be correct? Well, it's right here. It's basically saying that we're checking the invariance on the fees. So that's the thing that we just looked at. Because one of the things that happens is every time you harvest, you can change the protocol information, so you can like update the fees. We then figure out whether or not there's been any Algorand rewards that have been given to this contract, and we'll include those in what we send up to the protocol. We figure out what the protocol balances are. We specifically are interested in how much has been minted, and then we compute whether or not it's okay to be done. So we see if we're locked, we see if we've minted nothing, and if the pool balances are 0. And if so, we transfer the protocol balances to the receiver, which was chosen by the protocol. We emit the events, and then we continue. Notice that lots of variables say P at the end. That stands for prime. This is like a math thing. All right, let's look at withdrawing liquidity. I'm going in the order that the program's written. you might think, oh, we should talk about depositing first, but whatever. We're doing it in the order where the program works. So, when you withdraw, you have a certain amount of liquidity that you're withdrawing. So we figure out how much has been minted, and we figure out what percentage you are in that. So there's this function called bal's muldiv. So bal's muldiv, it takes in the liquidity that you're depositing, the pool balances, and how much was minted. So the pool balances is basically how much is outstanding. LP minted is how much has been minted. So therefore, we're basically figuring out what your percentage of that is. We can go look at this function, bal's muldiv. And it basically says that what we're going to do is we're going to have x and a and b, and we're going to figure out that, okay, well, here's your portion of a, and here's your portion of b. So what check muldiv does is it multiplies these two numbers and then divides them by that number. And so basically, this pool balances is the amount the pool holds in a and b tokens. And so we just take the two of them, multiply them, now we have this out amount. So then what we do is we compute the new balances. So we're going to have LP coming in. So we call the LP in function with LP. And we call the balances subtract function, which how much is going out. So bal subtract is right up here. So bal subtract, what it does is it calls balls f2. So this is a function that takes two arguments. So balls f2 takes a function, two arguments, and calls that function on the A piece and the B piece. So this is just a way to conveniently define a whole bunch of related functions so that we can keep the code size down. Because if your program gets too big, it's hard to understand it because you're scrolling through so much stuff. So we basically built a little helper library to write stuff like this. Okay, then what we do is we expect the user to have paid in this amount of LP, and then we pay out this amount of the out amount in balances. We emit, a withdraw event, and we update everything. Everything kind of follows the same pattern. Let's look at deposit. So deposit, you're going to put in some balances. So we're going to call the compute mint function, which I'll look at in a moment. And we're going to give it how much we currently have, what the balances of the pools. And then what we're going to do is we're going to say, okay, well, balances came in and LP went out. And then, who did this? It's this person. And so they'll have to send in those balances. We'll transfer the pay amount, and then we'll be done. And by the way, if we made a mistake on either of these two lines, then the verifier would throw an error. Just to remind you, what's LP out? It's LP mod, but it's doing with addition versus LP in, which switches the order. Because what these do is they basically are going to have a function that modifies the held, the HF, and a function that modifies the minted, the MF. And so we call HF and then MF. Now, when I say that, the verifier does things, so when you run this program, it compiles and verifies a bunch of things. So suppose that we're looking at the network token stuff. It's going to prove 434 theorems. And then when the token one gets compiled, it proves a different 585. And then the Triumvirate, it proves 173 theorems. And so there's a connection between these two things that is enforced by that. But remember that I alighted talking about the compute mint function. So if we go over to compute mint, you'll see that it's right here. So compute mint. So we get in the amount of that came in, the balances that came in, the pool balances, and the LP token. And so what we're going to do is we're going to split this up into A and B, and then the LP minted amount. So we're going to read off the minted part. Now, if we haven't minted anything before, then that means that this is the first mint. And so in that case, we're going to use the square root function. So we're going to take our two numbers that came in, and we're going to find their square. And then we're going to find the square root of them. And then we're going to, call that the minting. This is a cast, a downcast, and then we're going to return them. So this comment is just saying that well, these numbers could be the biggest possible thing, but that means that we would have max times max, and max times max when you square root it is max again. So that is the biggest thing. So that means that we know that this is safe. A verification claim gets generated here for that too, but this is just my informal thing to make sure that people understand why it's okay. But now that's the case where that's the first minting. Suppose you're not the first minting. Well, in that case, what we want to do is we want to say, okay, well, how much are the balances in the pools? And we'll figure out, well, how much was minted for A and how much was minted for B, what proportion of what you put in is what's already there. You just get the minimum of those. There are some, this is basically how Uniswap works. There are some AMMs that would return whatever extra you did, but we don't do that. And the reason that we don't do that is that our interface simulates running this code, and so it will do the right thing. So that means that anybody who would not be doing this wouldn't be using our interface, and so we're kind of immediately suspicious of them. So we'll mess with them and take extra money that they send us. By the way, when I say take extra money, that money, of course, goes to the pool. It doesn't go to the protocol. Now notice this function, compute mint. This is a reach function, but remember how I mentioned that we wanted to like expose all these functions for our interface? Well, that's what this does. This says that we're going to export that function. Because remember, when you write in reach, you just write in JavaScript. And so export is how you like define things for the external world. But when you're inside of reach, we know what the type of everything is. But when you go outside of reach, we don't know what the type is. So you have to explicitly annotate the type of things that you want to export. So we're saying we want to say that this function, compute mint, is a function that takes 3 balances and returns a number. And so that is used to basically protect the code that gets generated so that we can run type checking on it. So actually, might as well just show you that. So let's see, it's called build index.main.mjs. And so right here, this is this function, compute mint. That's the one that we just defined. And remember how it took 3 things, and those 3 things were balances. So see that the definition of this function is the very first thing that it does is it calls protect. And it calls protect with the value, v24, and contract 1. What's contract 1? Well, it's a description of a structure that has an A field and a B field where they're both contract zeros, and what are contract zeros? A number. So what this protect function does, here I'll show you, go to the docs. Well, let's just search. So what the protect function does is it asserts that a value has a certain reach type and exceptions that it's not. So basically what's happening here is that we're just making sure that we got called with valid things. We pull off the pieces. You can see in the code generation that, oh, it's checking to see if it's 0. And if it's not, and if it is 0, then, we call square root. And if it isn't 0, then we do the moldiv and then we return the answer. So that's kind of what's happening there. Let's go back to the code. All right, so anyways, so that was deposit. Boom, bada bing, bada boom, we're done. All right, now we're going to do the swaps. Now the swaps, because there are 2 different functions, they're swapping A for B and swapping B for A, we don't want to write the code twice, so we define a function to help us. So these functions, so we call this function called doSwap. What does doSwap do? So of course it's going to do the swap, and it's going to take a variable that says whether we're doing a swap from A to B or B to A. And one of the things that we do is we make it so that most things are the same between the 2, but some things are different, and this bool is for the different thing, but we like unify them. So like this thing BZA, what does it do? I'll show you. BZ is a function that takes a B value, it takes an A value and the B side is 0. AZ is a function that takes a B value and the A side is 0. So basically what this is doing is that doSwap is going to have its arguments are going to be whether it's A for B, it's going to have a normalized input, a normalized output, and then who is actually doing it. So anyways, there you go. Yeah. One thing that I forgot to mention with deposit is that, we made sure that it wasn't locked, because one of the things that you can do is the protocol can lock pools so that you can't put things in and you can't take things out. You can only, you can't do swaps and you can't deposit, but you can just take things out. So this is a way to protect liquidity providers. Okay, so now let's actually read the code for swapping. And I'll keep this down here so we can kind of like see the different examples about how it would be used. Let's center it like that. Okay, there we go. All right, so doSwap. So, we're going to make sure we're not locked. We're going to figure out what the pool balances were in the beginning. Then what we're going to do is we're going to compute the amount to swap. That's like the math, and we'll look into that in a moment. So remember, basically everything goes in, and the thing that comes out is a normalized output and how much from the pool goes to the protocol. We then update the pool balances after money going in, because we take the original pool balances and add the normalized input. Then who also got paid from the pool, so we subtract how much was the normalized output. Now what we're going to do is we're going to figure out afterwards how much from the pool went to the protocol, and so we subtract that, and and then we add to the protocol balances the pool to the protocol. So this is making sure that everything balances out. And remember, we have those theorems that make sure that all of these things stay in relationship with one another. So, if we made a mistake with any of these, the theorem would fail. And then we use that P nomenclature, right, to choose which one of these is we're supposed to do. Now, the last thing that we do is we make sure that the user's slippage was respected. And this is a check, so we call this function check balance less than or equal. That's what LTE stands for. So we make sure that the amount that they wanted to get out is less than the actual amount that they got out. Because the slippage amount is a lower bound. Because basically, if you walked up to somebody and were like, "Give me at least $10 for pesos," and they're like, "How about you take 100?" You'd be happy with that. You just don't want 9. Then the last thing that we do is we ensure that the pool ratio is preserved, and so compute k, like just multiplies them, and then we pay out the correct amount, and that's all that there is. So now we can, of course, go and look at the functions I skipped. So I skipped compute k, and I skipped compute swap. So let's just do compute k first because it's really simple. Compute k, you just multiply two numbers together. Easy. Compute swap, though, that's more interesting. Let's see. Compute swap. Boom. Right there. All right. So compute swap, it's going to get the normalized input and the balances and the protocol information. So it's a little bit hairy. So what we're going to do is we're going to say, okay, well, there's an input A amount and an input B amount, and a balance A amount and a balance B amount. And if we're going in the A to B direction, we make sure that no B's came in. And if we were going from the B to A direction, we made sure that no A's come in. Then what we're going to do is we're going to call this function compute swap 1. And it's going to be specialized for each thing. So it only looks at one side. So for instance, we're going to send in how much A came in, the balance of A's and the balance of B's, and then the protocol information, because that's where the fees are. And then from there, we're going to find out how much B comes out, how much from the pool to the protocol goes for A tokens, and how much from the pool to the protocol goes for B tokens. And now we're going to normalize this because we know that only A's came out, so that's going to be an AZ. And then we're going to capture these in the named functions. And then everything's going to be opposite for B's. So A's are going to come out, and the protocol B and the protocol A balances are going to come in the opposite order. So then we got to normalize them. So this is just a way to make it so that that do swap code can be the same, and we can isolate all of the things that differ from one side to the other right here. So now we can look at compute swap 1. So compute swap 1 is a long function. I mean, maybe you don't think it's long, but so it runs from line 218 to 256. I think it's the longest function that there is. All right, so what's going on here? So we're going to figure out the protocol fees, the protocol fee and the total fee. We have to figure out how much of the reserve came in. So we're going to use these terms, the amount that came in, the reserve in the input token, and the reserve in the output token. That's the balances of the pools. So we're going to add those up. Now we have to have a way of figuring out a way to figure out how valuable the thing that came in is. So that's why we've had this function called in to out new. So basically what it does is it says the amount that comes in, what percentage of the reserve output is that? And we do it based on the new exchange rate. Now what we're going to do is we're going to figure out how much came out if there were no fees. So this is the no fee output. So this is basically the value of the things that came in the output token. Now what we're going to do is we have to figure out the amount with a fee. And so what we do is we have this fee precision variable. The fee precision variable is like 10,000. I think it's 10,000. Oops. Fee precision. No. Fee. What's it called? It's called fee. There you go. See, it's 10,000. Okay. So then we figure out how much the fee is. So we take the amount, we make it a big number, and we take the precision and we subtract the total fee. So that's the contribution that you make as a swapper, because the amount that you paid as a fee doesn't count for you. Then what we do is we take the amount that came in and we scale it by the same amount. then we can add those together. And this is basically how much is now in the protocol um, that has the fee part taken out of it. So then what we can do is we can figure out how much should come out if there would have been a fee. And so there's what we do is we take the amount in, okay, with the fee included, multiplied by the reserve amount, and then divide by this, since this is the proportion of the total thing. This is that big theorem that I mentioned before. So this basically says that we want to assert that that amount must be less than the maximum. And yeah, prove that. Okay, so now we know that yes amount. And by the way, this theorem satisfies the downcasting requirement here. So now what we can do is we know how much you would have got if there were no fees, and we know how much you get if there is fees. So now we can figure out how much the fee actually is. So we figure out how much the fee is by subtracting them from each other. Because we know that no fee out is more, so we subtract that, now we know that. So now we can figure out the percentage of that fee that goes to the protocol by just using 100. And this gives us the, what we ultimately know is that we now have the fees on the input side right here and on the output side, and we can normalize those to compare them in just out. And so now what we do, the protocol is going to collect whatever fee is worth more. Now it says whatever fee is worth more. It turns out that when one fee is not worth as much, it's worth 0. So we're basically making sure that the protocol actually gets a fee. So we just get the fee in and fee out. So that way, one of these is always going to be 0. So you can never pay. The protocol can never collect a fee from the pool, and both sides, it only takes it from one. And yeah, this compute swap function, we do the same, is thing, where we say that we're going to take these arguments and we're going to, call the compute function and return them, and we generate the code for that. So anyway, so I've actually now walked through everything because that's the swap is the last thing, and at the end the protocol can delete the pool, and that burns the rest of the supply and destroys it. And this, by the way, generates a verification constraint that it actually has everything. So yeah, so that's the code for pools, and we covered everything there. I do want to talk about the details of the triumvirate, because it's in this file and it's kind of cool. So we'll head up to that code. All right. So the basic idea of the triumvirate is that its job is to receive protocols that get registered so that everyone can find out about them. That's kind of its main job. But its other job is to be able to collect the protocol fees. Now, rather than build a big complicated DAO where there are like governance tokens and stuff like that, which we want to do eventually, but we want to simplify things. Right now, there's just 3 people who can do it. That's the triumvirate. And so these are, Crassus, Pompey, and Caesar. If Caesar proposes something, then Pompey or Crassus can support it, and then it will run. But Caesar can't propose something and support it. And we also want to be sure that if Caesar proposes something, and then Crassus thinks that he's supporting that, but Caesar changes what he's proposing in the meantime, that Crassus will only support what he thought what he thought Caesar was going to do. So that's kind of like the constraints of this. So these commands, these are the things that can actually happen. So there's a no-up, which means nothing, you don't do anything. Triumvirs, you can propose new people to be in charge. You can propose a new protocol information, and that new protocol information includes replacing the triumvirate with a totally different DAO. And then you can also harvest from particular contracts, and you can collect rewards that have been accrued to the triumvirate itself, and then you can kill the triumvirate. So basically, just kind of like looking far forward into the future, like what's going to happen is that we're going to make a new DAO. We're going to make we're going to send new protocol information, which is going to have the identity of that new DAO. Then we're going to harvest from every single pool and tell them about the new DAO. Then we're going to kill the DAO, and it's going to be over. And then now, from that point on, the DAO with governance tokens, that will be the one that's in charge. Okay, so basically the main things that I want to talk about are the proposing and the supporting, because that's really where all the interesting stuff happens. There's, of course, a view, there's who the initial triumvirs are, there's the initial protocol information, But the main thing is that there's this array of the commands that are going to run. And the commands start off as no ops. And what happens is that we're skipping that, we'll come back to it. We're going to prove the invariant that the balance is always 0, the fees are valid, and the commands that are in memory are also valid. So let's stop and look at what that means. So in's commands means that each one of the commands satisfies the in command thing. In command, that's invariant for commands, is that if you're proposing new info, the fees are valid. Otherwise, we don't have any constraints on it. You can do whatever you want. Okay. And we run until we're done. So we already looked at the register function, so let's look at propose. So what propose does is says, are you proposing a valid command? Are you one of the triumvirs? If so, set your command to whatever that is, and then be done. So what is the check triumvir? It basically says, do you have an index in this? And if you don't, then you're not one of them. And that's all that there is to it. Okay. Okay, now next, there's supporting. So supporting says you have to say who you're supporting. So I'm supporting Crassus. Okay, and so we check to make sure that you are a triumvir, that you're not supporting yourself. We go look at what command the other one proposed. We make sure that the command that you expect, E stands for expected command, matches that command. We change the command to a no-op because it's been done. And then what we do is we evaluate the command. So there's this function called eval command, and it's going to return a new done, new triumvirs, and new info. So what does eval command do? Well, a no-op does nothing. New triumvirs replaces the triumvirs. New info replaces the info. So those are kind of boring. Harvest is the interesting one. So what harvest one does is it says, okay, well, there's some contract, there's the token B, and the receiver. So we'll construct a remote object. Then what we're going to do is we're going to switch on whether there is a token A or there isn't. If there is, this is basically a trick to have the same code happen in two places. So that's what Go does. So we're going to send in the assets, token A and token B. We're going to include some fees, and then we're going to call the harvest function. And we're going to say, here's the receiver, and here's the new info. And then that's it. What rewards is going to do is it's going to get any funds that are untracked. So these are things that were sent to the triumvirate behind the scenes, and we're going to transfer those to the receiver. And then finally we can kill, which just returns true. So that is the whole shebang. That's the whole thing. I did, I didn't go into detail about all of the general tools. There's like, there's a min function, there's a max function. Those are not part of reach generally. And then I skipped these checking functions. So basically what these checking functions do is like check add does an addition, but first checks to see if some property holds. And we only do this check if verifier arithmetic is on, because otherwise we don't need to do it. Because these checks, by the way, are to make sure that the verifier is happy. The program will error the same no matter what. It's just a way to check errors. And and then there are a few functions for dealing with the the data structures that I mentioned before. And then of course, there's a very important variable that the triumvirate is made of 3 people. And notice that I haven't talked at all about some other things. So there's of course, there's a test suite, and that test suite is this file. So it's 2,000 lines of code. And there's actually another test file for the staker. And what this does basically is there's this thing where we can create new scenarios and run lots and lots of related scenarios. And then the other thing that I didn't talk about is I didn't talk about the code that actually runs in your browser. And so we have a whole other repository for that. And the interface to the contract code, I mean, it's just these functions that say API. So there's the provider function, so provider _ withdraw and deposit. There's trader, swap A and swap B. And then there's also the view function. And so there's this info function, and then there's the similar ones for the triumvirate. So only these functions are the things that are called. Everything else we don't need. Actually, I guess there's one more thing, which is that we need those exported functions. So there's compute swap, and then the compute mint. And so the interface will just call this thing. It'll call the view, get the information about the pool you're looking at, call compute swap, figure out what the swap is going to be, and that's the UI that you get sent. Yeah, and that program is like a normal, plain Jane, React program. I mean, maybe I shouldn't call it plain Jane. It's a beautiful, wonderful, awesome React program. But I didn't write it, so I can't really like go through all the details of it. But yeah, so I hope that you found it illuminating to see what a big, complicated reach program looks like. But it's only 537 lines. It's not that bad. I feel really guilty when I show programs that are more than like 100 lines of code. Yeah, the actual swapping code right here, it's 200 lines. That's not bad. And then we specialize it for the two different sides of the code generation. Then the core math logic of this is these. What is that? Like another 100 lines of code? Looks like that's about right. And then the triumvirate, it's about 130 lines, looks like. Yeah, so it's pretty nice. I think that if I wanted to make this code shorter, I definitely could. There's lots of comments, and I don't really like comments. And there's lots of really, really long variable names. But sometimes you gotta please other people, and so that's why I named these things like pool to proto B. And by the way, I keep implying that like I wrote this, but a few people had their hands in this thing, but they have to answer to my taste, and so that's why I would normally insist on really, really short variable names, but whatever. All right, so I think this is all I want to say about it. I'm happy to answer questions in the Q&A or whatever. And if you want a tour of the React code, maybe we can have Christoph go through that separately. All right, peace out.